and welcome to Doolittle Institute's Technical Showcase event series. I'm Sonia Slater. I'm the Tech Transfer Project Coordinator here at Doolittle. And it's my pleasure to welcome you all to the September installment of this series. The Doolittle Institute is an Air Force Research Lab Innovation Institute and a DefenseWorks Innovation Hub, partnered with the Air Force Research Lab Munitions Directorate. We support the Munitions Directorate by working to license and commercialize its technologies in the private sector through technology transfer, by identifying and fostering new relationships through innovation and collaboration, and by developing today's students into tomorrow's STEM workforce. The goal of the Technical Showcase event series is to strengthen and broaden science and technology collaborations among industry, academia, and the Department of Defense through a monthly topic-focused interchange, thus providing opportunities for the government to share its research and technological needs with industry and academia, and for industry and academia to showcase their cutting-edge technologies and capabilities to government stakeholders. I'm pleased to introduce our government speaker for this month's topic area, Advanced Scene Generation, Mr. Robert Bobby Watson. Mr. Watson is a research engineer for the Seeker branch of the Air Force Research Lab Munitions Directorate. In this role, he serves as a scene generation technology lead, guiding development of modeling techniques required to represent munition sensors and targets. To accomplish this, Mr. Watson's research focuses on accurately predicting radiometric phenomenology necessary for research and development of seekers and algorithms in a variety of environments, especially real-time hardware-in-the-loop facilities. He also serves as the principal loop simulator facility, aka K-Hills. K-Hills serves as a test bed for leading-edge munition technology and a developer of advanced test capability used by agencies across the country. If you have any questions for Mr. Watson, please post them in the chat window. These questions will be read following the presentation. Mr. Watson?
All right, we're going to go ahead and share the screen, so bear with me, everyone online. All right, I hope everybody can see the screen. If you can't, go ahead and put it in the chat window. But thank you for the introduction, Sonia. As she said, my name is Robert Watson, also Bobby. No one actually called me Robert, so it's always a fun thing to have that be my actual name. But we're here to talk about advanced scene generation as part of the Open BAA topics. I'm going to dive into a couple different aspects of this, tie first to the mission of our lab, then I'm going to dive a little deeper into what is scene generation to give a better idea. The goal with this being to give people an understanding of what it means when we really talk scene gen. And then we're going to dive a little bit into what hardware in the loop is, because a lot of companies, they may be doing things that represent some interesting aspects of scene gen, but then they don't understand what the mission is, what the test technology we're trying to develop. And so we're going to try and tie all of this together to give a good base level understanding of what it is this topic area is deeply interested in. So we'll start here. So I work for the Munitions Directorate. So the way that the research laboratories for the Air Force are broken up is that there are 9 base technology directorates. Each one focuses on a major aspect for the Air Force. So you have something like the Aerospace Directorate out of Dayton. You have the Sensors Directorate, also out of Dayton. And then for us, we have the Munitions Directorate out of Eglin Air Force Base, with a focus being on munitions. The mission here being to discover, develop, integrate, demonstrate, and transition conventional air-launched weapon technologies, enabling the Department of the Air Force to dominate across all domains. One thing not on this chart is that the lab is constructed as a one lab, 2 services approach. So we are both supporting the US Air Force as well as the United States Space Force. So what I'm listing here are the 2023 priority areas for our Munitions Directorate. We're going to focus here on 2 key aspects that would tie itself to scene generation, but you could tie scene generation, after I talk about that, you could tie it really to the network collaborative autonomous weapons, counter-air, counter-maritime, enabling, air-based defense. Honestly, it applies to all these different things because of how it fits into these 2 categories. The first one is foundational weapon S&T. So when you think about foundational weapons S&T, you're thinking about warheads, you're thinking about seekers, you're thinking about airframes, you're thinking about controls, navigation, all these fundamental capabilities that build out these weapons. But there's another foundational aspect. being able to test those brand new amazing capabilities. And that's where our area sits in, is we are developing those next generation of test technologies to build up and actually expand upon what is happening and being able to prove that what the S&T who created that really cool new tech, it actually works. And so we work heavily with the Seekers branch and autonomy, navigation, controls, and computational engineering to examine those algorithms and make sure those seekers are working the way they say they are, and it builds a fundamental level of trust. And so that's how big thing that we do to support that. And so these whole, that's going to then apply to any type of weapon that would come in. So when we do something with scene generation, a lot of times people like to ask me, well, can you narrow it down to a specific type of system? That doesn't end up happening. We are building test technologies, means we don't get to narrow down. We have to be nice and big and broad in what we're trying to accomplish. This is now really leaking into digital material management, which is the process of integrating and employing digital methodology across life cycles of weapons, where people are building up these new digital models, these new digital capabilities, these new digital testing things. The digital twin is an outstanding concept that everyone seems to focus on. And it's the idea of building these digital replicas of physical assets. And when you build a digital replica, you still have to test it. And how do you test these things? You have to build digital representations of physical hardware, and then you still have to feed those digital representations the data that would code to a physical system. So these two fundamental areas are where we tend to sit. We talk to a lot of people in digital simulation and foundational weapon S&T. So that's where our area sits, but let's go into a little more about what is scene generation. What you can look at it is we're a subset of a subset of a subset of different foundational capabilities. We all know that we all work with computers, we have graphics cards in them, we've seen what visualization and things like that do, but for scene generation, we are really the process of using the signatures of different real world phenomenology to make a representative digital world based on physics. Those last three words are absolutely critical to every single part of scene generation. If it's not based on physics, you are not going to be accurate. You're not going to be able to do a proper test of anything that's coming out there. Excuse me. So how do we make these types of scene generation? Well, a lot of time we take data to the digital world and put it into real systems algorithms for development and testing. We're going to talk about that when we get to hardware in the loop and software in the loop and the other big concepts and capabilities, but we try to make sure we have to build these out. So an example here would be an infrared. So on the side here, you see a picture that discusses the electromagnetic spectrum. We tend to focus in that ultraviolet, visible, infrared, and radio wave. We don't do anything with microwave, but for different types of analysis of where we might build scene generation. So for infrared is very similar to visible, even though you can't see it outside of, say, using night vision goggles or something like that. With infrared, we're going to create that physics-based world in three-dimensional space, and then whatever sensor, or let's just use a camera for this example, is looking out, it's going to be looking at a 2D snapshot of that world from a perspective. So in infrared, if we were to feed that to a sensor, we would take a picture with that camera, that fake camera, and that would have to include everything that would be part of infrared, your temperature profiles, your material properties, everything that ties all this together. And so that would be what scene generation is. Now, when you're doing it, you have to be energy conservative. So energy conservative is a common term when you're talking about finite element analysis for actual, oh goodness. Names are escaping me because it's not what I'm talking about today, but CFD for computational fluid dynamics, structures, finite element analysis for structural analysis. You always have to stay energy conservative to ensure that what you are solving is giving you a proper solution, and that if you're doing something in time, you are not adding energy or subtracting energy from a system, because that doesn't, you can't create energy from nothing. And so energy conservative has to be very consistent when you're working in scene generation. Now, RW, our area of interest is fairly broad for advanced scene gen. And this is a scene in the kind of the topics we're looking at. We look at the electro-optical, which is like infrared, ultraviolet, visible light. But we also look at radio frequency, and something we've been picking up lately is magnetic. So there's actually been a topic that was an STTR a few years ago to build a magnetic simulator, and we are now looking in, there's a future topic potentially coming out that's going to be on magnetic scene generation as well. And so we're looking at trying to establish all of these different topics to build out these capabilities. But the big takeaway from this chart is visualization does not equal scene generation. Visualization, so for those to put this in perspective, visualization is kind of like a video game, making things look really pretty, really close. You think of Call of Duty, Modern Warfare, you think of these things, they look very, very accurate. And what they do is they take corners on the physics to make the physics as representative as possible without having to solve the fundamental aspects of physics. In scene generation, you can't take that leap. You have to do the physics. So, some common challenges that are faced. Scene generation is a constantly evolving, constantly developing field. We are having to constantly look at the fact that technology and seekers and sensors is always looking at, from an IR perspective, more pixels, but from everything, it's just getting bigger and bigger scope of what we can look at. Frame rates are going faster. Scene content phenomenology is being added. Faster computational speeds. What that means is really like real time. Now, a key word here is real time. For a lot of people, when they look at things and they think real time, they're thinking either into that real time refresh rate for say a monitor, which could be 60 hertz, 120 hertz, 240 hertz, or they're thinking real time as in like wall clock speed. You're thinking 1 second in simulation time is 1 second in real time. When I'm thinking real time, I'm thinking about whatever unit under test was and what the speed of that sensor seeker is. And that could be much faster than what you consider real time or what you consider relative to you. And so we have to be able to meet the needs of those as they come up. Now, as we build these out, another big issue we always come into is the availability of models, the data scarcity. You can see this was discussed ad nauseum in the collaborative ATR capability test that was run here at the Doolittle Technical Showcase a few months ago, which, while a video was not available, Dr. David Gray's charts are available on the website, and they detail a lot of this data scarcity. And besides even finding the data, the next step of if you have the data is V&Ving of those models, making sure you know you're accurate. And so with the increase in leveraging of AI and ML to fill in the pieces, that's a fantastic thing. We look at leveraging more AI ML capabilities, but anything you leverage something in AI ML, you have to be able to be A, repeatable, because if you're doing something that's an actual test, you can't do it 4 times and get 4 slightly different solutions because the AI ML made a small adjustment each time. It has to be consistent, number one. And number two, I have to be able to V&V those models to something. I have to anchor it. And so you have to be able to prove your AI is anchored in real truth and then get that to be consistent when you run the simulation. And that can also tie into building out those material property databases and the bands of interest that you're caring about. And then also a big thing here is because we're talking about those fast speeds and we're talking about anchoring models and material properties, scene generation tends to be not simple at all and require a high level of expertise to be done correctly. You get people that are experts in computer science and people that are experts in physics. And you have to tie them together with each other, because getting somebody who is a master of all of these is a very difficult capability. A person who is an expert in understanding OpenGL, Vulkan, CUDA, and can tie those in together and maintain real time and reduce the amount of interrupts and everything else, who also is an expert in every aspect of those physics, that is not a small task. And so building out the teams and building out these capabilities is key and is critical. And so I'm going to give an example of something that we have done at RW that I am also the program manager of to show you how some of this works. And so here we have something called FLIGHTS, or called the Fast Line of Sight Imagery for Targets and Exhaust Plume Signature. For all the engineers on the call, It's my favorite thing. It's an acronym that we create the acronym and then backfill it to make it look pretty, but we want to make the acronym work, so we do that. I apologize, I make lots of bad jokes. It's how I keep people engaged. So you're going to see here, you have 3 different key things that we're doing. Well, so we take in our phenomenology, which is your objects, your backgrounds, your plumes, your scene dynamics, your countermeasures. You incorporate those with your environmental effects, your atmospheric, your solar, your environmental lighting, your clouds, and then any optional sensor effects, jitter, noise, optical blur, all of those together, plus any other different user-defined functions to create a scene. And then that all has to be done at potentially 1,000, well, we'll just use an example here, 1,000 frames per second. So in 1 second, I have to do all that math at 1,000 for every 0.001 seconds. And so to do that, we leverage the GPU. So you can see here at the bottom right corner, this basically we call it our Flights processing pipeline. It's a really good representation where Flights has an API driver on the CPU that uses plugins. And we don't need to dive into, we're not going to dive deep into Flights, but the idea is we leverage plugins that all move onto the GPU and leverage the different GPU capabilities to maintain that speed. And we're able to hit those frame rates, and that's how we've been able to do a lot of these different things. And we leverage different aspects of OpenGL graphics language. I'm not going to get into that here today. That's a whole other presentation. But the key here is how this ties together is these are the things that we're thinking about when we're running SceneGen. We're trying to make sure that we can maintain all these physics while also diving deep into getting that speed where we want it to be. We include all the important phenomena in the infrared, visible, and ultraviolet spectra that emit, absorb, or reflect electromagnetic energy. And we use highly developed specialized codes to make sure we get a realistic representation from a seeker sensor perspective. And we have done this over 30 plus years in the lab. Yes, it was done before me because I definitely have not worked 30 years in the lab, but point still stands. It has been some really good work that we have done over the years. And this is a good example of what we have done to meet IR scene generation needs and what we can do going forward. So that says a little bit about what SceneGen is and what we're trying to do. Now let's get into the why. So it was mentioned in the introduction about hardware in the loop. And hardware in the loop is a big part of what we do, but it's not the only part. So here are really the 3 cruxes that everything that we do in SceneGen feeds. Number 1 is that desktop, that high level on our pyramid, and there are modeling and sim pyramids. There are pyramids everywhere. So of course I'm going to make really a terrible looking pyramid, but it's a pyramid nonetheless. Desktop phenomenology analysis. So what does that mean? So if I create concepts and new algorithms and new capabilities, I need to feed them to prove that they're working so they can move to the next stage. They can go into seekers, they can go into sensors, they can go into the next aspects. So if I'm going to do that, I need to be able to do those top high-level analysis and feed that data. Next, when it actually goes and builds these digital models and goes into, say, a digital twin or a digital examination of something that might become something else, we got to move into those high-fidelity digital simulations. That can be your software in the loop. That can be other testing. That is a key component of building in so you can finally get to that prototype capability. And so you go through here, you go through those high-fidelity digital sims, until finally you reach this real-time synchronized hardware in the loop testing infrastructure. And we're going to dive into what hardware in the loop means because there are a couple different things that I want to dive into, but all of these are critical to RW. So when you're looking to build proposals or build capabilities, we have to think of all 3 of these, and really that bottom takeaway, they call them bang boxes, sometimes bullets. My big takeaway from this chart is to provide a common resource to support all phases of weapon testing. That is critical to RW, and that is what we are trying to do, is we need to hit that bottom bullet hard. And so that's what we have done with Flights, and that is what we are trying to do in every different part of the electromagnetic spectrum. So that's the why. And so here we're going to dive into hardware in the loop because people are familiar with desktop phenomenology. They're familiar even to an extent of thinking of building a digital model and testing it. But unless you're in this world, you're not familiar with hardware in the loop. It's not something taught in college. It's not something taught in all these classes. It's something that you go and you pick up and you learn how to do. And so we're going to just do a quick walkthrough, and then I'm going to talk about the facility we have to give you an idea of why this is important. So basically in Hardware in the Loop, so over here you can see in the top right-hand corner a flight motion simulator. So you're going to have something like that that's going to hold your unit under test. You have a real-time simulation computer that everything is being fed into. You could also have even a runtime visualization capability, but that real-time sim computer is going to manage everything. So that unit under test sitting on the table is going to receive an input from a projector or any other device there. It's going to feed that information to that real-time scene computer. That real-time computer is then going to take that data and feed it back to the guidance system. It's going to go into a GPS simulator if one is needed, and it's going to go into SceneGen. And each of those things are going to start processing, and they all have to process and finish at the same time to feed back in at the refresh rates of the unit under test. So the sensor and target state are going to get fed to the SceneGen, which is then going to take that to make a radiometric signal, which is going to go through a projector control system to be calibrated and turn into a proper image to be fed into a projector, which will then have a radiometric target image displayed to your unit under test. In that same time, the state and time is going to be fed to a GPS simulator, which gets that antenna input, and the flight motion simulator commands are going to do all the calculations to give the guidance system and say what happens to everything else, because you're only looking at that unit under test, but there's a lot of other things that go onto a platform when it's being tested. All that information is fed at the refresh rate. It would then the unit under test gets to make another decision and immediately go and do the next step. Now, what I've just described is called closed loop hardware in the loop, where I would not have any input on what's happening. Everything is being controlled from that unit under test perspective. I am outside the loop. There's another way we do this called open loop, where it's a little less powerful in that we don't necessarily know if every aspect's working, but if we know how we want this thing to move, we can potentially pre-run all the scene gen to then make a pseudo real-time scene generation. The problem is that if I do that, I will not be able to do something. It will only follow the route that I have predetermined and given it. So open loop can be useful, but it doesn't tell you the whole story. That's why closed loop hardware in the loop is such a powerful capability and something that we constantly try to make sure we leverage in developing things and developing different capabilities. Next chart. Said next chart while also controlling charts. So that tells you where my mind's at. So this is Cahill's, or the Kinetic Kill Hardware in the Loop Simulator Facility. This is a facility based at RW. This is where I work. And it provides AFRL with a hardware in the loop capability for non-destructive evaluation of integrated munition guidance, navigation, and control concepts. So the whole point of this facility is we are providing the AFR with these next generation test technologies, and we're developing them. You can see in that middle image on the right-hand side, a picture of like doing a panoramic dome where you can actually have some come in. We've done different things to support that. There's a picture of our actual flight table in the top right-hand side, pictures of our projectors on the bottom right. But the whole point is we have RF chambers, we have large HPC resources, we have real-time computers, target simulators, synthetic scene generation, flight motion simulation, a world-class staff, and we can even do distributed connectivity to build into these kind of distributed events and support all these different things. And the goal here is this lab is designed to support and develop and test technologies, as well as testing other things that may come into the lab. And so this is a really outstanding facility that we have built up and worked with over the years. I'm going to finish this up here. I should have put on here, but I didn't because I made the chart and I forgot to put it on there. Link to the Open BAA on the Doolittle website, but on our collaborators here, I've put our section chief here, Captain Ryan Trenner, and then there are some other people that have supported me with RF and magnetic information. So RF is Mr. Robert Barton and Mr. Cinque Jose. They tend to talk to me a lot on that, and Mr. John Grimes has been talking with us about, he has been leading some of the magnetic scene generation capabilities. And so we have been running these efforts and building these up, and I hope that this provides a lot of good information, and we're going to move into the Q&A session.
Okay, thank you, Mr. Watson. And now we'll go ahead and check our Q&A. we have any questions out there? So I have not seen anybody post a question. This is an open time frame right now to ask Bobby Watson if you have any questions on the presentation. So I do have a question to prompt.
Okay.
Cahill's, where is this?
It's actually located in Building 13, which is RW, where RW is at on Egwin.
Okay.
So we have, that is in, it's one of the only labs left in the actual Building 13 facility.
Okay. Do we have any other questions from the group?
I do have one, Bobby. The question is, what is the most challenging domain to work on RF, IR, viz, et cetera?
That is a tough question. I would say it would probably be in the RF spectra, or so for RF, because when you do RF, you're solving Maxwell's equations. And when you, so one of the topics that we've seen, if you look at the SBIRs in the past, there's been a topic on real-time RF scene generation, and figuring out how to do some of those things are very difficult, which is why we've leaned on SBIRs in the past, and we still look at some of those capabilities.
I do have another question in the chat. Do you collaborate with DIME and GWEF?
Yes, I speak with Brent Wagner of DIME, and I also speak with the GWEF.
Another question in the chat. Are you leveraging any existing engines such as Unreal, Unity, etc., or do you use one developed in-house?
So Flights has been developed in-house. We have looked at leveraging other engines, but for internally, so for IR, we have been leveraging, mainly we've been developing in OpenGL and Vulkan and actually building off our own engine. But I am not opposed to leveraging other engines if they have better capabilities. And I'll speak to that here. If you ever watched the show Scrubs, there's a scene where the janitor character has a wrench and he decides that he's going to make a new tool, and so he duct tapes a knife to it and he goes knife wrench, and it is a tool that he uses to do multiple things, and at one point he goes to holster it and stabs himself in the leg. And so I'm never opposed to building out and using other tools if it makes sense and it is what it is. I fully support people presenting whatever tools they are leveraging. I will look at what is the best option and the best opportunity going forward. And also, I apologize, I said Brent Wagner, but he doesn't work for the DIME lab. He works for another facility, but I do talk to the DIME lab.
Another question for you, Bobby. What is DIME?
That was answered in the chat afterwards.
Right. Another question. Thanks for the description of your work. How would you like us to engage with you if we think we can provide assistance?
So I believe for that one, you'd reach out to Miss Aisha Hyder of Doolittle, and she would connect for further questions and comments, so you can set up an actual one-on-one discussion with me to understand what some of the capabilities you have are and where we would go forward with that. And we could have those discussions in a more appropriate setting where we could talk controlled and classified information like CUI.
So if I can pull on that one just a little bit, is it more of software side? Is it more of hardware development? Is it more of engine, database, V&V? Is there a specific area you're interested in collaborating with people, or all of them?
So hardware I don't tend to get into, because when we do testing, there's a whole separate field dedicated to developing test systems in the different bands. What I'm focused on is the software. And so developing software capabilities in bands of interest is where I would really like to see a lot of those capabilities. And software can mean many things. It can mean developing engines or other capabilities there. It could mean developing methods for adapting and building out models. It could mean finding more efficient ways to ensure that you're staying physically accurate in your models. But building into that software mindset, it gets wide because we have such a wide variety of things that could come into like the Cahill's facility that we have to meet the needs of.
So if I could make the analogy that the Cahill's facility itself is like an oscilloscope that's testing equipment, and you're working on the software features built into an oscilloscope, rather than the oscilloscope itself.
Yes.
Okay.
Scene generation is needed to make these things work, but without the other things, I can't do the hardware test.
Bobby, a couple more questions in the chat.
Okay.
First one is, you briefed common challenges. However, what are AFRL's biggest challenges and what are your priorities on the support and capabilities needed from the industry?
So I'd say some of the biggest challenges, honestly, you're going to see a lot of them come out in SBR topics because we tend to put them there as a way for us to get some really innovative ideas from different small businesses. But you're going to see in so in those challenges, you're going to see really it comes down to building out those different wave bands and so we have a really good understanding of IR. That does not mean that that is the only method we would ever use to do IR. If you have something you think is even better, I'm always willing to listen and learn and understand. But I would say that it would be I understand that people always want to narrow it down of what are the most specific, but I would say if you look at what we've advertised in the past, like RF is always a big one, magnetics becoming something we're trying to understand, visible is something I'm always intrigued by and trying to understand, and that's the difference between visible and visualization ties into that because visible scene generation is going to tie in that physics and other capabilities that go into real light, like the real visible spectra, whereas visualization is, again, that making things look good, but not necessarily being physics-based accurate. Does that answer that question? Hope that answers the question. I hope that answers the question that was asked.
And then you're focused on the software side of things, but that's not to say that there's not hardware needs as well, so.
Correct. You see
all aspects of that continuum, this is just a software-focused portion of it?
100%. You'll see a lot of things that go out. I know that Mr. Justin Meadows, who is our IR projector lead, and he has done a lot of different topics. He has research going ongoing. He has SBR topics that people submit to try and get a better tackle on just what it is to be IR projection. And we do the same things with RF. We try to make sure there's a wide variety of topics out there to constantly get small businesses in the mix, as well as get our own standing up internally to try to make sure that we have a good detailed understanding of where things are, the next cutting edge in generation.
Bobby, another question in the chat. Is there interest in high fidelity scene capture, generation, and manipulation that can result in high fidelity rendering in simulations such as neural radiance spheres?
There very well could be, but at this time I am not aware of something that I could answer that question effectively.
Okay, another question from the chat. Can you elaborate on what physics-based entails and what the most important aspects are? Is it more important to have accurate location information, for example, tied to GPS data from the sensor, accurate material properties of objects, or accurate representations of surfaces and spatial relationships?
So I would say the second two are going to be the most important. When I say physics-based, I mean that if I were to take a flat plate, let's go with IR. I've got an IR black body that's 1 meter by 1 meter that is at 300 Kelvin. When I take that object and I point an IR camera in a representative waveband at it, like a real waveband, go out and get a FLIR, we'll use the example here of FLIR, get a FLIR camera and look at it, I will see a signature of a specific number. When I go and do the calculation and I finish it in this, I will follow the physics that's in optics books and things like that, and I will get an answer. The image that I saw with a real camera that measures IR and the image I made in my scene generation must be the same. So that means the material properties must be the same. That means that you need to, so here's where the art comes in. So one of the amazing things in scene gen, it's very similar to finite volume and finite element analysis, meshing techniques, is that scene generation is both a science and an art. And the reason I say that is because there is a science with making sure you remain physics-based accurate, but the art comes in to, you don't necessarily have to be super detailed. Like if I'm modeling, we'll use myself as a category, I don't need to model down to the specific hairs on my head, but I need to model enough of my hair to make sure if there is something signature related to my hair that I can capture that signature. And so what is the level of detail that I have to have? that is critical to the art of all the scene generation. And so that's where some of the physics, you still have to model the physics, but what is the acceptable level to make sure your unit under test is being tested appropriately?
And then with the scene, you're also incorporating external influences as well. So you have to capture all the nearby sources of IR that would also be projecting on that scene, not just what you're projecting or what you're sensing. So
Yes.
that problem balloons very quickly.
Correct. So there are things that capture environmental lighting. You have reflections. With ray tracing, you can get more accurate shadowing, things like that, which can potentially change some of this. There's a whole lot that feeds into a composite signature. And if you think back to that flights chart, you can see all the different things that come into play. With that simple test case, it was literally, I was just trying to make it as simple as possible, where it's a flat plate. And everybody can do a flat plate if they've gone through some basic electrical engineering or physics-based courses.
Okay, I want to thank Mr. Watson for his presentation today. Everyone's welcome to contact the Doolittle Institute at the tech transfer at doolittleinsitute.org if they'd like to engage with Mr. Watson. Also, if you're interested in future collaborations with the Air Force Research Lab Munitions Directorate through the Air Delivered Broad Agency announcement to develop munitions and other technologies, you should contact us to schedule a meeting. We are looking for partnerships with industry and academia in areas such as autonomous target recognition, sensors, navigation, and cyber resiliency. We also have licensing opportunities available. To stay current on our upcoming technical showcases, please join our ecosystem at doolittleinstitute.org and follow the Doolittle Institute on social media. There will be many future opportunities for industry and academia to engage and submit applications to highlight their innovative technologies and capabilities, and to learn more about what the Munitions Directorate and other DLD collaborators are working on. Additionally, Mr. Watson's presentation and a recording of today's event will be posted on our website. Thank you for your attendance today. Have a great afternoon, and we'll see you next time.